that is. And so I'm going to try to help you with it, but I will tell you that you're probably going to have to do some of this on your own, because I think it's just a subject that you need to kind of step by step go through it. So, countercurrent multiplication is the way that our body really concentrates urine. In other words, it would be nice if we said, okay, we want to pee urine that's 1,200 milliosmoles. Let's just pump out enough water or pump in enough sodium to make it 1,200 milliosmoles, which is really concentrated. The fact is, our pumps aren't that strong. We can't pump it that strong. So we use this technique called countercurrent multiplication that allows us to pump it to like 200 difference from one area to the other, but because the water is moving one way and the filtrate's it's going the other way, it gradually builds it up so it can create a very concentrated urine. So let me show you two things. I'm going to go through this on the quicker side, I think. But this is in RC Bio Group, okay? So you've all got access to it. And if you go to links, and that's where I'm at. Let's go back here. Oh, damn it. I hate it when I do that. And the reason I hate it is because I've come up with a new password that is 1.5 miles long.
I think you're secure.
Well, I kept getting, oh damn it, something wrong. I kept getting these notes that said, well, it's not long enough, it's not secure enough, you need to have a number in it, you got to have a capital letter in it, you got to have a symbol in it. I said, screw that, I'm coming up with a universal password that has everything in it, and that's it. All right, so here we go. Go up here to Sites. That takes, the only group I'm in is RC Bio Group, and maybe the same holds true for you. Then go to RC Bio Group, go into RC Bio Group, go to links. All the videos are under links. When you get into links, you'll see this big long list here, and go down to where it says renal system links. Amazing, huh? Renal system links. And then go to this one here that says countercurrent multiplication explained. Hey, how's that for a deal? Okay. Shut up. Activate Adobe Flash. I hit the wrong button. All right, so allow it. Okay. So this is a little animation thing that you can work through very quickly. I'm going to run through it really quickly because this is the whole deal. The idea of this whole system is to create a very high osmotic concentration down here in the lower end of the loop of Henle. Okay? So we know at the proximal tubule up there it's about 300, which is basically normal in all of our cells. It's going to come down here, it's going to work its way back. As it comes down, it's going to become progressively more concentrated. But as it goes back up, it's going to become less and less concentrated once again. So at some point you're going to say, well, why do we do that? What good does that do us? So I'm going to try to show you that. Let's go through this animation really quick.
Functional distinctions between the descending and ascending limbs of the loops of Henle of juxtamedullary nephrons are critical to the establishment of the vertical osmotic gradient in the renal medulla. The descending limb is highly permeable to water and is the only segment of the tubule that does not actively extrude sodium chloride. The ascending limb actively transports sodium chloride out of the tubule and into the interstitial fluid. It is always impermeable to water, so salt leaves without water osmotically following along. Even though the flow of fluid is continuous through the loop of Henle, we will visualize what happens step by step. Before the gradient is established, the tubular fluid and medullary interstitial fluid are isotonic at 300 milliosmoles per liter. The active salt pump in the ascending limb transports sodium chloride out of the lumen
So we can
until the
pump it to a
surrounding interstitial
concentration of
fluid
200
is 200
to
milliosmoles
400.
per liter more concentrated than the tubular fluid in this limb. Water moves passively out of the descending limb until the osmolarities of the fluid in the descending limb and the interstitial fluid become equal. We now advance the entire column of fluid in the loop of Henle. The ascending pump again transports sodium chloride out while water passively leaves the descending limb until a 200
300 to
milliosmol per liter
500.
difference is reestablished
Still
between the
just a
ascending
200
limb and both the interstitial
difference.
fluid and the ascending limb at each horizontal level. As the tubular fluid advances still further, the gradient is disrupted once again at all levels. Again, active extrusion of sodium chloride from the ascending limb, coupled with the net diffusion of water out of the descending limb, reestablishes the 200 milliosmoles per liter gradient at all levels. As this process continues, the fluid in the descending limb becomes increasingly more hypertonic until it reaches a maximum concentration of 1,200 milliosmoles per liter at the bottom of the loop. Because the interstitial fluid always achieves equilibrium with the descending limb, a gradient is likewise established in the medullary interstitial fluid. In contrast, the concentration of the tubular fluid in the ascending limb progressively decreases as salt is pumped out and water is unable to follow. Note that even though the ascending limb pump can generate a gradient of only 200 milliosmoles per liter at each horizontal level, this effect is multiplied into a large vertical gradient because of the countercurrent flow within the loop.
Because this is coming
This
down and that's
concentrating
going up.
mechanism is known as countercurrent multiplication.
Okay. Now, you guys can watch that again and again and again because it's on RC Bio Group if you like. But if you just think about it really carefully one time, you'll have it down, what he just said. Now, the question that I always used to ask myself is, what the hell do we do that for? If all we're doing is going to concentrate it up to 1,200, and then we're going to take it back down to 100, what have we done? Because it's still going to come out here and become urine. So what's really going to make, how are we going to be able to concentrate urine based on this thing? Well, the answer is this. The answer is what we're trying to do here is create this zone of very high hypertonic tissue right in here, interstitial fluid that is very, very concentrated. And if you could take a bite of one of your medullas of one of your kidneys, one of your little pyramids, it would be extremely salty at 1,200, okay? Now, so that's where I always had the struggle, and so from that I'm going to go back to my lecture series and show you two slides that I think will make it understandable as to why we really do this. Okay, as I said, all of this countercurrent multiplication thing in this loop of Henle, all it does is create a very high tonicity zone here in the middle, very high levels, from 300 at the top to 1,200 down here at below. But the fluid that's in the duct comes down and gets more and more concentrated, but then goes up and gets less and less concentrated. But wait a minute. Remember, the fluid has to make one more pass through this area in order to get out, okay? And that last pass is where everything happens. He didn't even talk about it in that multiplication thing we just saw. So it's these two slides here that I think make all the difference. So what happens is we've done this, we've created this high concentrated zone down here at the bottom. And now our fluid goes back to the top. It's gone back up to about 100, 200 up here. But wait a minute, it's got to make one more trip out, okay? And that trip is down through the collecting ducts. And the collecting ducts have these little doors on them. They call them aqua doors or aqua pores, I think. I think of them as aquadors. And the aquadors allow the water that's inside here to diffuse out. Now, if the water diffuses out, then this becomes very concentrated urine right here. So if you have doors that you can open along here that let that water rush out, then it leaves it very concentrated, and lo and behold, we're dumping it into the pyramid down here at the bottom, and you've got very concentrated urine in your bladder now, or going down from your pelvis down your ureters into your bladder and out. So the whole thing that this was created for was to create that high concentration zone down through here so that it could make that last pass. Now the thing about the last pass is that these aquadors, these little doors that are coming down this collecting duct, are controlled by one thing. They're controlled by ADH, okay? So this slide here is in the presence of ADH. In the presence of ADH, the doors are open. And that allows the water to come out, and when you get the water out, that leaves nothing but salt in here, and it's very concentrated. Okay? So ADH opens the aquadors and lets the water out, which then produces this concentrated urine. Now what happens if we don't have ADH? Well, if we don't have ADH, we've got this picture. So we have this picture over here. This is in the absence of ADH. In the absence of ADH, the doors are all closed down here, and the water, which you had up here at 100 to 200 milliosmoles, comes down here, but the water can't get out, and so therefore it just continues to come on down here, and it remains very, very dilute. And out it comes, and you produce large volumes of very dilute urine. In other words, you wasted this high concentration zone that you had created down here if you don't have any ADH.
Would that dehydrate you?
I'm sorry?
Would that dehydrate you quicker too?
I'm sorry, say it again.
Dehydrate, would that dehydrate?
You would dehydrate very quickly, yeah. If your urine is just flowing out and it's all very, very dilute and you're making tons of it, and this person here with no ADH is making tons of urine, which is very, very clear and very, very low, 1.0001, yes, you're going to get very dehydrated very quickly. And what do we call that disease when you don't have any ADH? Diabetes insipidus. Diabetes insipidus. Remember, diabetes mellitus has to do with sugar and insulin. This is diabetes insipidus. It's a totally different disease, not even related. It's called diabetes insipidus, where you're just pouring out dilute urine. Okay? So that's the reason for this countercurrent multiplication that we just talked about. Countercurrent multiplication just means the fact that because the two things are moving in opposite direction and it can only pump 200, it can still get more and more and more concentrated by just pumping 200. Okay? Yeah?
It has to do with the same reason why caffeine and alcohol make you pee, right? Don't they have some...
No. No. Caffeine and tea and all those things are diuretics. They basically poison your tubules up high, your proximal tubule, distal tubule. They make it so they don't do any of this, and then just the water just comes out.
Okay.
It doesn't reabsorb the water, and out it goes.
Does it inhibit ADH production at all?
No, it doesn't affect ADH really, other than in response. If you're peeing out really dilute urine, your ADH is going to turn itself on to try to keep you from peeing out that much more. Okay? All right. Now, some of you folks heard me make the point at the beginning of the term, and I know it was very hard on some of you, and I apologize for that. But I said that there's some topics in this subject and some questions that I put on the tests that are designed for only one thing, and that is to separate the sheep from the goats. You remember that?
Oh, I remember.
Oh, yeah.
distinctly.
Yeah. Well, and I have to tell you that the reason that story came up is because I've used it for a long time around here. And a couple of years ago I used it, and this girl wrote me a really sweet note at the end of the term and thanked me for this and thanked me for that. She said, and by the way, in case you didn't know where the sheep or goats comes from, and she had some biblical scripture that describes the difference between the sheep and the goats and how, you know. My dad, when he was in the 7th grade, he was put in with the goats, and because he didn't know how to do math. He never did. He never cared about it. Never did. And so he was in this little town in southern Arkansas, and he was put in the goat class of 7th grade instead of the sheep class. And he wore that burden his whole life until he got out of college and had a master's degree. And he came back and he found out that the president of the bank, the local bank there in that town, was also one of the goats in the class with him. So the point being, it doesn't really matter whether you're a sheep or a goat in the end, and it matters how hard you work and how it all works out. Okay? Anyway. Yes?
Okay. Which one's better according to this analogy?
Sheep are supposedly better.
Because they are
But
dumb
don't take it
as
too.
rocks.
Don't
Well,
take
let's
it
not,
too far.
we're not going to debate this issue anymore.
No, I wasn't sure. I was like, yeah, I'm a goat. Wait, I don't want to be a goat?
No, you don't want to be a goat.
But I don't want to be a sheep.
You don't want to
Well.
either, okay?
Can I be a
I don't
llama?
want to be a
I
llama.
want to be an alpaca. They always look like David Bowie.
All right.
I'll be an alpaca. I'll pack in my bag and get out of here.
I just want to be a nurse.
Now we're going to go to chapter 27.
Did you?
All right. Slideshow. Start.
What you're doing is you're creating high in here.
Does it push it out?
So this process is to make this high. So this,
Oh, I see.
and this has nothing to do with what's the
It's
height
just
or
when it gets
everything
pushed
to
out
do
to
with what's
the
in out here. And then we're using
When it
this
comes
to
to
make the
water,
Yeah.
diffuse.
Yes.
exactly in order to
That
make
makes
it here.
I think I heard your question and answer right.
No,
Okay,
thank you.
here we go.
And it took me a second to, I was like,
Why is that so big?
okay. Because this part is
Yeah.
low.
And this one.
This would be low. It would just be, you know, whatever. Who cares? Yeah, usually not happening. It would just be kind of here.
Okay, is there a computer genius in the room that can tell me how to make the picture smaller?
So maybe tomorrow. I'll probably do
That's
it.
basically all I'm doing.
Yeah.
You're gonna do it so many times.
All I'm doing
He
tomorrow.
changed the way. I did it once before. I can't remember how
How to do it though.
All I'm
And then
doing
Thursday or
tomorrow
Friday, I will probably do it. I will. Unfortunately, I don't have a weekend.
Now you're back to.
All this term.
Well, I had to do when it goes to the collecting side, and the donuts.
Anyways, yeah, so I filled up like the first 4 or 5
There you go. There you go.
to my, the best of my knowledge.
As with most computer problems, if you just turn them off and turn them back on, they work right. All right, here we go. Let's run through this chapter. This is really an important chapter, and I've always thought when I teach this chapter, we get to the end of it, y'all really don't have a clue what I've talked about, even though it's pretty darn simple. And so what I've done is I've come up with what I call a clinical conference. And I was sitting at the beach yesterday in our little new motorhome, and I filmed a clinical conference for you, okay? And then I posted it on YouTube, on the PCC STEM 1, that site where a lot of other lectures are posted. And it's called Chapter 27, Fluids and Electrolytes Clinical Conference, I think, something really a little obvious like that. So, after you've seen this lecture today and thought about it, and maybe even after you've read the chapter 27, you may want to watch that. Because what that talk does is it goes over a series of cases that are basically fluid and electrolyte screw-ups. People that have got one disease or another that has given them either a severe metabolic acidosis, metabolic alkalosis, respiratory acidosis, respiratory alkalosis, all four of them, and then a couple more just for fun that I think will help you understand this concept of fluids and electrolytes a little bit better. But let's start with the basics here. First of all, we're talking about water more than anything. Water is a big deal in our bodies. Most of the fluid that's outside of our cells, which is extracellular fluid, is water and not much else. The cytosol, the cytoplasm inside your cells is mostly water as well. We call that intracellular fluid because it's inside cells. The stuff on the outside we call extracellular fluid. We're going to talk about these. Everything that happens in our body pretty much completely depends on water. We don't, everything's in a solution, and that's how the reactions occur, is because they're in solution. And of course the water acts as a diffusion medium for gases, nutrients, waste products, and so forth. So, the carbon dioxide, when it diffuses out of the capillaries, it's got to diffuse into something, and it's diffusing into water, and vice versa. And I am out of power.
Need batteries?
Just a minute. I've got better than battery.
Just got a second remote.
I've got another one of those things. Jeez. Well, my 232 class had their second exam today. Boy. Whew. I hope they
Was it the endocrine?
get it figured out. Yeah, they struggled. It was on endocrine and special senses.
Endocrine was rough.
All right, so anyway, we talked about the importance of water, and what we're talking about today is how does our body maintain the right amount of water? And indeed, what is the right amount of water? Because we have to have a normal amount of intracellular fluid and extracellular fluid. Now, when I say those words, those are really easy to say, but what do they really mean? Let's kind of split them up and help you understand it as we go through this. Fluid balance is what we all maintain every day. We drink a certain amount in, we pee a certain amount out. We sweat a certain amount out, we poop a certain amount out, we bleed a certain amount out. We have ins and outs every day, and that's what we're going to be talking about here a little bit. But every day we have to sort of balance out. And of course, if we're low on water, our brain gets the idea that, hey, we're low on water, and we get thirsty, and we go drink water. And you guys have probably all been in that situation where you're just so damn thirsty, you could drink 2 or 3 quarts of water in one sitting. I've been there, and you have too. But that's all just your body telling your body that, hey, we need to fix this. So that's what it does. And not only do we have to have the total amount in our body right, but we have to balance the right amount between our intracellular and our extracellular fluid compartments. We call them compartments, even though that's kind of a vague term. The digestive system is our primary source of water gains. Very few of us walk around every night and stick an IV in our hand or in our arm and give ourselves a couple of quarts of water. Usually we just drink it. It's a whole lot easier, right? And our urinary system is the primary way in which we lose it. Now we do lose it in other ways, and we'll talk about them, but the primary way we lose is through our urine. And as we've been talking about, our urinary system can control how much we lose. With ADH and with all of this, this filtration and secretion and afferent and efferent arterioles and all these controls that we have on all this stuff, we can control it. Electrolytes are things that are a little salt, little minerals or ions that are released. So when you dissolve some sodium chloride, some salt, it dissociates into sodium and chloride ions, and that's the way they stay. They stay as ions in our body most of the time. the definition of electrolyte is it is something that allows you to be able to conduct electric current. If you had pure water, electricity wouldn't flow through it. It has to have some electrolytes in it to conduct electricity. The electrolyte balance is also important because not only do we have to keep the amount of water normal, but we got to keep the amount of the electrolytes normal. So we have to take in the right amount of sodium and then pee out the right amount of sodium. And our body can control that mostly without us thinking about it much. Most of the electrolytes get absorbed in through our GI tract. You eat a salty set of McDonald's French fries and you've just had 1.5 grams of salt, and you're going to have to do something with that. You're going to either have to, if you need it, you're going to keep it inside of you. Most of the time you're going to pee it out. And that's why you get those big Cokes that have about 9,000 calories of sugar in them if you drink the sugary ones. We'll talk about McDonald's before this is all over. Electrolyte balance obviously has to be kept straight. And by the way, you know, we also lose at our sweat glands. If you go out and exercise on a hot day, you can be pouring out 4 liters an hour. You can sweat 4 quarts an hour if you're really going for it. Obviously, one other aspect of this is our acid-base balance, because we know, I've talked many times this term about how we always have to keep our pH right. We have to keep our pH right at 7.4 or nothing works in our body. Same as we have to keep our temperature right at 98.6 or nothing works. So our body is continually, all the time, making acid. Okay? And we have to continually be getting rid of acid, and indeed every minute of our lives we are getting rid of acid. How are we getting rid of acid?
Breathing out.
We're breathing out CO2, which came from carbonic acid, which is getting rid of the acid in our body. All the chemical reactions that are going on in our body are generating acids as waste products, and we have to always be getting rid of them. We also get rid of it in our urine to some degree. But let's just say that the most important way to get rid of acid is by breathing. And we'll come back to that. So what do the kidneys do? What do they offer us? Well, kidneys can get rid of hydrogen ions, which is an acid as well, right? Hydrogen ions, that's the definition of acid. That's where the H in pH comes from, remember that? pH means, what does pH mean?
Power of hydrogen.
The power of hydrogen. Never heard it referred to as that. It's the concentration of hydrogen ions to the negative log. It's a negative 6, negative 7 means 10 to the minus 7.
Right.
10 to the pH of 6 means 10 to the minus 6. Hydrogen ion concentration. You thought you could forget all that damn math and all that scientific notation and all those powers of 10 and all that stuff. No, you gotta still know it. All right. So our kidneys can get rid of hydrogen ions by secreting them. Remember, secreting is when we're actually pushing stuff out. It does it in the distal parts of the convoluted tubules and some in the collecting system as well. The lungs are the #1 place to get rid of CO2, which is acid as well. Water accounts for about 60% of a male's body weight, 50% of a female's body weight. Now, why is that? Why is there a difference there? Why would men have more water and women have less water?
Fear not.
Because men have more muscle mass and people have more adipose tissue.
So women are fatter and men are stronger. Exactly right. I'll keep that in mind.
Depends what kind of man you are.
Yeah. All right. So most of our water in our body is intracellular. In other words, it's inside the cells. So all that water that's in those muscle cells, that's all intracellular fluid. How do we move it between the intracellular fluids inside the cells and the extracellular fluid outside of the cells? Well, we do most of it by osmosis. The simplest way of moving water anywhere is by simple diffusion from an area that's more concentrated to an area that's less concentrated. Remember, this is an important concept. Remember that we have pumps. We have pumps that can push potassium one way, that can push sodium one way, push chloride one way. We have all these pumps for electrolytes, but we don't have any pumps for water. Okay, the water always simply follows the electrolytes. Okay, we just don't have any water pumps in our body that can pump water out of a cell or pump water into a cell. The only thing we can do is pump sodium in. For example, if we pump enough sodium into a cell, the water will come in following it. Make sense? Okay. So the major subdivisions of the extracellular fluid, the fluid that's not inside the cells, the main two places we find it in our body is in the interstitial fluid. There is water around every cell in our body. It's just a tiny little rim around there, you know, but you add it up for all the cells and it ends up being quite a bit. The other major subdivision is in the plasma. Remember, you took that tube of blood and you spun it down, and if you took this tube of blood, you spun it down, and about 45% of it down at the bottom was RBCs, and 55% above that was plasma, right? And you remember that 45% number, also called the hematocrit. Okay. Now, so that ends up being a fair amount of fluid, and it's circulating around your body all the time, so it's movable and so forth. What are other places that we find extracellular fluid?
Lymph.
What?
Lymph.
Lymph?
Synovial fluid.
Synovial fluid in our joints.
Aqueous humor.
Aqueous humor in our eyeballs.
Cerebrospinal fluid.
Cerebrospinal fluid. All right, so you know, there's a bunch of them, but all together they don't amount to all that much. Lymph, perilymph, endolymph, that stuff in your ear canals. Remember the semicircular canals and all that jazz. Cerebrospinal fluid, synovial fluid. Have you been looking ahead? You just look ahead on the slides, don't you? Come on, Daisy. Daisy.
It's in the book.
Daisy. Okay, it's in the book? Okay,
Yeah, we
good.
just
Okay. Serous fluid, pleural fluid, pericardial fluid, peritoneal fluid, and aqueous humor. So that's kind of most. That's most of them right there. All right. So how does the fluid really move back and forth? Well, most of it moves in and out of the capillaries, the tiny blood vessels. Remember, that are only one cell layer thick. They're simple squamous epithelium, right? And fluid can go in and out through them. So water can come out of your blood vessels and go out into your tissues, same as the gases and so forth. And then the lymphatic systems that we just mentioned. So what are we really made up of? If you could take us and boil us down or something and get rid of everything, you'd find out that if we, average person,